slightly different than originally announced. I'd like to acknowledge my co-authors, Peter, Youngshon, Edmunds, and Stantec. So I'm going to go through the background objectives, introduce some of the model design, and discuss a little bit about inflow, salinity, flushing, and nutrient loading, and evaluate some comparisons really simple between model and data, discuss the submarine light and seagrass attributes, and summarize and give the significance at the end.
Turn the mic a little bit towards you. Bring it down. Bring it down.
Okay. So the SALINITY is directly influenced by freshwater inflow, and seagrass appear to require at least 20% of surface light, but light extinction is a combination of chlorophyll, color-dissolved organic matter, or CDOM, and turbidity. And so freshwater inflow, salinity gradients, flushing, submarine light, seagrass survival are all interrelated in some places like we are in South Florida. And all of these things are very non-linear. And that's why we use models to link physical, biochemical, biological processes. We can assess relationships between the experiments where we manipulate inputs and outputs, and then evaluate alternatives. So our objectives, again, was simply just to develop a model to systematically transport biogeochemical processes, generally Seagrasses in the Caloosahatchee Estuary in 2002-2009. And we're going to examine inflow, flushing, nutrients. So here's the Caloosahatchee Estuary. So we split into three segments. Another segment that goes from S79, Estuary, down just a little beautiful island. Middle segment, which is in green on our screen, is up there, that goes from the boundary at the top to an area between two bridges. And the third segment that runs down from the boundary at the second to Centerville Bridge that's bound to the north by Pine. So these are 14 boxes that we use for development of box model, which is a model to look at the exchanges. We use RTIS. So we use RTIS to interpolate a bunch of data and come up with these volumes and average depth for these segments, calculate the distance along the longitudinal and have an area of polygons. We also have an approach that Youngshon developed to predict salinity in the Caloosahatchee time series of daily salinities for each of the segments from 2002 to 2009. So here is the average salinities of those segments. So we have a biogeochemical model of the phytoplankton, which is their loss terms, respiration, sinking, exudation, mortality, go through a converter to derive organic nitrogen and organic phosphorus. Phosphorus through the phosphate is available for uptake. Nitrogen neutralized ammonia. This NOx is a combination of nitrogen and nitrite. So those things again are available for uptake. There is nitrification, which is a linkage for the oxidation of ammonia into nitrate with the source term there, and a sink called denitrification, which is a net loss of nitrate from the heat system. The particulate matter, and organic nitrogen, organic phosphorus, there is a sinking, a gravitational loss to the benthos. And there's a dissolved exchange for phosphate, ammonia, and nitrate, a sediment water exchange that we based on some empirical data. Collected and averaged by the segments. And finally, the horizontal exchanges of downstream flow and then net bidirectional exchange across the segment boundaries was done using the box model. So sort of a schematic showing all three segments, segment 1, 2, 3, each has one of these biogeochemical models in it. We have freshwater inflow, so this is the daily time series at S79 based on data from 2002 to 2009. We also have lateral inflows, which is abbreviated TGW, and stands for varies in groundwater. So we have a model in order to predict the amount of fresh water that comes in laterally to each sediment. The box model gives us the net effective or downstream exchanges shown at the top here, which is Q zeros. And there's also, again, this bidirectional balance, which is the term we often use as dispersion between the two adjacent boundaries. As I mentioned, we have a salinity time series, daily time series in each of the segments. There's also an S4, which is salinity in the downstream boundary. Finally, this downstream segment includes models for Thalassia and Halodule. So a lot of boundary inputs. These are monthly concentration profiles, and it's hard to see. These go from 2002 to 2009, 96 months, and then monthly data about the inputs that came from Lee County, also from the South Florida Water Management District database. Here again is Q0. Those are shown along this side. So here we have ammonia, NOx, phosphate, organic nitrogen, organic phosphorus, and chlorophyll. These are all the Qs. The lateral inputs, TGW again, so this would be segment 1 for each of those constituents, segment 2, and segment 3. And the 6 variables that I just mentioned, these are concentration plots. So what we do is multiply the concentration by the flow, which is cubic meters per day. We get loadings for each of these, both the upstream end and laterally in grams per day. Instead of chlorophyll, that's in milligrams per day. So Peter and Bob Chamberlain did a series of comprehensive studies of seagrass salinity effects. And among the species they did were Halodule and Thalassia. So this graph just shows the range of experimental salinities from 0 to 35, and a relative factor here that ranges from 0 to 1 on the y-axis. And that Halodule is a hyperbolic relationship. And we can see here that here's the growth equation for Halodule, Pmax, maximum growth rate, and the radius or light function, a biomass feedback, there's our hyperbolic salinity function, exponential temperature effects, and then the sheet biomass of the plants. Similar approach for Thalassia, except instead of the hyperbolic equation, it's sigmoidal relationship. And this is the exact same response that Serengeti exhibits, which we use over on the East Coast in Southern Lagoon. Same equation structure, except we have the sigmoidal parameters instead of hyperbolic ones. So these are monthly salinities for the whole estuary from 2002 to 2009, shown as the open circles in a line with the left y-axis. The right y-axis has discharge and CFS, and that's shown as the shaded area behind it. So you can see we have high discharges in 2003, 2004, 2005, and very, very low during drought periods in 07 to 08. Over here we have the negative exponential relationship between salinity on the y-axis and discharge. And overall flow conditions for these 8 years, 9 years, 8 years, you see that the average salinity of the estuary is 11, but it fluctuates a lot, from very low levels to very high levels, depending on the flow. And the bottom panels are flushing time. You can see that this has the same discharge as the top panel. And flushing times in days. This is done through a freshwater replacement method because we have salinity gradients in the estuary. When we know the inflow, we calculate the time it takes to replace the entire freshwater volume of the estuary. And it ranges from very low levels during high discharge of approximately 10 or less days up to almost 100 days during the drought periods. And you can also see that it's very dependent on the discharge rate. So very low inflows, either during drought or during dry season, it's a lot longer to flush the estuary and vice versa. Overall flow conditions over this whole period of record that we're interested in, the average flushing time at Caloosahatchee is about 34 days. So it's approximately a month, depending on your assumptions and the different approaches that you can use to measure how the water mass turns over in the estuary. These are similar graphics for nutrient loads. The top panel is nitrogen in grams per meter squared per day. This is per meter square of estuary surface area, not the watershed. In-situ nitrogen loading follows the discharge very closely. You see a generally linear relationship, although it sort of breaks down at higher inflows. Similarly for phosphorus, phosphorus does not follow as closely as nitrogen. You can see that there are times where inflow is very extreme here in 2004, 2005, and the phosphorus loading doesn't track that exactly. You can see that out in this part of the graph. So at low discharges, the phosphorus loading matches it, but at high levels it doesn't. And we've seen in different types of analyses that the Caloosahatchee estuary is comparatively insensitive to phosphorus loading and patterns of phosphorus concentrations in time and space. It's much more of a nitrogen dependent system. So I'm not going to go into too much detail. I think there's a lot of stuff going on. Generally, the segments are segment 1 across the top, segment 2, segment 3, from 2002 to 2009. On the left here is the total light attenuation coefficient. When we overlay some points here that are average, we only have light data for 2005 just into 2009. This is average daily light attenuation. You can see just visually that it does a good job model. Probably better in the lower segment 3 than the upper part. We don't have a lot of light data to calibrate this model. Similar layout, but this is average, monthly average concentrations as the line from the model, and monthly average concentrations from the field for the points. This is organic nitrogen in the middle, and chlorophyll on the right. And in general, the model underestimates organic nitrogen concentrations in the upper segment here, both during the wet period and the dry period. And by contrast, it sort of underestimates only during the wet period in the lower estuary. The model does a good job with chlorophyll, considering all the assumptions involved, all the various rate processes that affect the amount of biomass in the estuary, and really the overall simplicity of model formulations. It does a good job in replicating product range. The only one is we do overestimate in-situ concentration slightly in the lower segment. Similar ammonia here, nitrate and phosphate for the 3 segments, 1, 2, 3. Ammonia is complicated, it's very difficult. In terms of faster than any other pool in the estuary, it's very difficult to get a handle on it. Considering all the assumptions and data availability and the formulations, the model does a good job with ammonia. It really does well with nitrate. Nitrates are very much dependent on freshwater inflow. That DIN plot I showed you earlier, a lot of the inflow DIN relationship is due to the effects of nitrate in that population. And here's what I mentioned before about phosphate. It's a fairly flat line. You can see a little bit increase in phosphate concentrations during the drought period in the upper part of the estuary. But in time and space, phosphate doesn't vary nearly as much as the other constituents. Here's our Halodule model. We have data on shoot biomass, and this is in the lower estuary, so the shaded area shows salinity in the 3rd segment and the downstream segment. We have shoot biomass data from 2004 to 2007. Biomass in grams per meter square is comparatively low for Halodule. It's sort of a pioneer species, and that's depicted here because the model does a good job with the magnitude of the biomass in the shoots. But it misses the timing, so we hit this minimum in 2006, but the Halodule really recovered quite quickly in 2007. The model response was not as fast. By contrast, Thalassia, first of all, has a lot more shoot biomass. Thalassia is a climax species, has a lot more root rhizome biomass, and therefore a lot bigger shoots. And we can see that it's up to about 400 grams carbon per meter square. And the model does a good job with the timing. Here with this peak in 04, the minimum in 06, and then again rising at the same rate as the field. But it overshoots it just slightly. So we get a little bit of mismatched magnitude in each third class. Okay, there's a lot going on this one. I'm going to try to get through it here. The top panel, segment 1, segment 2, segment 3, from 2002 to 2009. The heavy dark line is average daily light attenuation. This is the total light attenuation coefficient shown on the left y-axis, ranging from 0 to over 5. This is the reciprocal depth. The second are the shaded bars. So these are annual composition of the total light attenuation coefficient. So these are the percentages due to chlorophyll in green, color shown in yellow, and turbidity shown in white. And this is listed by axis here from 0 to 100%. And the third thing is just the inflow, which is the average daily inflow shown as the shaded area on the right side. So to summarize this one, inflow, of course, is much greater in the wet period than the dry. 2003 to 2005 was high, 2007 2009 more of a drought stage. Total light attenuation higher in wet season than dry, increases with freshwater inflow and greatest in segment 1. It's the overall highest values from the black line and top end. Color greater in wet years, greatest in segment 1. And then we have some different percentages of the total composition of the light attenuation coefficient. So color is greatest in the upper estuary in response to freshwater inflow. Chlorophyll A, by contrast, is greater in dry years, has much more of an effect on total light attenuation in the lower estuary. You see upwards near 35% in segment 3. And finally, turbidity is greater in dry years and also greatest in segment 3. Upwards of 25%. And just as a quick aside, this model does not predict turbidity. We use monitoring data from the estuary multiplied by a coefficient that then calculates its effects on light attenuation. So the representation of turbidity is really dependent on the data that we have and also the effects of chlorophyll, because remember, these are relative contributions. So chlorophyll has more higher predicted effects, turbidity is going to be a little bit lower. So here are this total contributions to light attenuation that are averaged by segment and season, dry versus wet. And overall, you can see again, light attenuation is greater in the wet season. That has a lot to do with the effects of chlorophyll. It's increased in the wet. It increases in the downstream direction. Color higher in the upper estuary, lower in the lower estuary. Overall, over 50% of light attenuation in this estuary, both wet and dry seasons, is due to the effects of components on organic matter. And for more details on this, there's a poster number by CHNEP that goes into much more in situ and empirical data that resulted in a CNOP study of the Caloosahatchee. So what we did was we took the total time of the model and queried the output, the daily output, for all values that were greater than or equal to 20% light at the bottom of the downstream segment 3. And we used that as a metric to determine what the most optimal or most desirable conditions were. So you can see freshwater inflow. We only had 107 days out of 2,922 days where light at the bottom of segment 3 was greater than 20%. So inflows range from 0 to 335 CFS, salinity average 26, depth was about 1.5 meters, and we had 22% of the surface area at the bottom. Chlorophyll, I want you to sort of look at chlorophyll and total light attenuation here. Chlorophyll in segment 3 is about 3.2 milligrams per cubic meter with a light attenuation of 0.6. So we did this in this modeling framework, and we were able to duplicate what was done in a field study that used the resource requirements of the seagrasses to come up with very similar values. So we have a box model of the Caloosahatchee that's combined with a simulation model to look at transport. We have several water column constituents, 2 seagrasses. And the fit between the data in the model varied by season, segment, and different constituents. We've come up with some evaluation of the light extinction coefficients with color being on the upper estuary, turbidity and chlorophyll more so in the lower estuary during drought conditions. And in segment 3, about an equal contribution of each of the 3. You see that to get 20% light or more in the lower segment, chlorophyll values need to be less than about 4 milligrams per cubic meter. Light extinction about 0.6. And the model is a research tool. And again, to explore these relationships, we're conducting a lot of experiments about loading and we're evaluating different management alternatives. And I know that this talk was supposed to be about flushing time when I originally wrote the abstract. We have another study that we published on nutrient budgets, discharge, and flushing in the Caloosahatchee in the same piece. So if you want a copy of this paper, send me an email, cfsl@sfwd.gov, and
I would